analysis with a large energy emissions model. A little background first on Environment and Climate Change Canada. Its mandate is the preservation and enhancement of the natural environment, and part of that is estimating and measuring greenhouse gas emissions. I'm not on the measurement side of things. I'm an economist. We generate emission projections using the historical data that a bunch of engineers estimate and measure. The emission projections, emission projections have been produced and published since 2011, which is the year I did my co-op term there. There's been a few different climate plans in the interim, and every couple of years we submit our projections to the United Nations. But we update them annually. We update them with new revised historical data, as well as new assumptions and adjusted assumptions as needed. This is a diagram of the model we use. It's two models working together. There's Energy 2020, which is a consumer choice energy model, and then there's a macroeconomic model. And when they operate, they kind of iterate and they pass back and forth different variables. Yeah, that's that. So yeah, the reference case 2024 is our latest set of projections. It was submitted in the Biennial Transparency Report to the United Nations. And for every reference case, we do a sensitivity analysis where we vary GDP and energy prices. And a new area of research is on uncertainty. So this is an old comic that I found in my first when I showed up at Environment Canada in 2011, and it was in the modeling room. The model is developed on an old programming language called Promula. It's a variant of Fortran. And so as I was getting familiar with the model, it seemed very mysterious. I couldn't get it to work the way I wanted to. It was always creating errors. And anyway, so this comic was it really spoke to me at the time. But what I learned was that the model actually was deterministic. And so when you're operating it correctly and you're using the same inputs and assumptions, you'll always come up with the exact same point estimate in the projected period. And so here's a few different projections from reference case 2024. On the side there, you've got megatons of carbon dioxide equivalent, and you've got the historical period. There's the black line, and the projection starting here in 2023. And the central case is that blue one with measures, and it goes up to 589 megatons in 2040. And then you've got a variety of different sensitivity scenarios. And again, these are all point estimates with just different assumptions. So, uncertainty analysis is a new area of work that we're undertaking, and so it gives us an understanding of how emission projections might deviate from a baseline, and then it can be used in policy analysis for developing contingency plans, and it also enhances their credibility, because whenever you show someone a point estimate, they're like, well, that's pretty precise, you know, but it's not really realistic. So an algebraic approach to measuring uncertainty is not really feasible due to the size of the model. There's over 100,000 lines of code. And so we're trying a numerical approach using the Monte Carlo analysis. You could conduct a Monte Carlo analysis with the model itself, but runs take over an hour to complete, and so it's not practical to conduct a large number of runs. So we introduced this probabilistic analysis in the Biennial Transparency Report, estimating the uncertainty around GDP and like future economic activity and energy prices. Yeah. So we did this by generating a quadratic function to simulate the projected emissions from E2020. This is an important point. In this work, we're just looking at the consumer choice energy model, Energy 2020. In the future, we're going to expand it to include also the macroeconomic side. And the work was conducted by my colleagues Richard Laferrière and Marshall Long. So I consulted on it, and I'm here presenting today, but it's not the core of my work anymore. here's the method we use. So we calibrated a quadratic function using the reference case and the high and low GDP growth sensitivity scenarios. Oops. We test the quadratic function against 4 novel scenarios out of the model, and we assign a probability density function to it, and then we run the Monte Carlo analysis, and then we repeat this for oil and natural gas prices. And once we're done, we combine all the quadratic functions to estimate the uncertainty in respect to GDP growth and energy prices. So calibrating the quadratic function, it's of this form, and we're using again the reference case, the high and the low GDP sensitivity cases. And then we introduce the variation, and it's just a simple application of a scalar. And so here's some results, and we see that the elasticities from the calibrated quadratic function are similar, and the errors are small. You can see in column 5 there we've got elasticities. The top part is the results from the model itself, and then the bottom part is the quadratic estimates and the novel scenarios that we're testing against. And here's a handy diagram which goes over it in a diagram form. So we've got the novel scenarios are the orange dots, and then the blue dots are the actual results from the model, and then the quadratic trend is there, and it's not quite going through all the dots, but it's pretty close. So next we're going to assign the PDF, and using a Shapiro test, we can't reject that a normal distribution isn't suitable. Thus, we assign the normal distribution. It's got a mean of 0 and a variance of 0.026, and that's we used in this case. This is the GDP growth one, so we're using historical estimates of GDP growth and measured against forecasts. And so then we use Monte Carlo analysis to run that equation 40,000 times to get some results. And then we're taking the results and we're combining the point estimate from the reference case. That's in equation 2. And then equation 3, I had to look this notation up. That's capital Pi. It's just a simple. It's a compounded growth notation. So the argument is that we're introducing into the quadratic is the compounded economic growth over time. And we repeat this procedure for oil prices and for natural gas prices, and then we combine them all into equation 4. And here we got some results. So on the side are the frequency. That black dotted line in the middle, that's the reference case, our central case in the United Nations, UNFCCC, it's called a with measure scenario, so that's the WN there. So this is 2030 emissions. It's for Canada, 626 megatons. And then we have the confidence interval at 5%, we got 609 megatons, and up to 646 megatons for 95% interval. And comparing this uncertainty with our sensitivity results, we see you get a pretty good result. So I've stripped away the scenarios that fall in between, but in the middle there we've got the reference case. So this is these are the sets of projections which I presented on slide 7 earlier. And at the top we've got the high GDP growth, high energy price scenario. At the bottom we've got the low GDP growth, low energy price scenario, sensitivity scenario. And we see the confidence intervals land at 646 megatons there in 2030, so pretty close to the high case. The bottom case there at 609 megatons. So we think that the uncertainty analysis we're doing is producing usable and interesting results. And the work continues. So it's a pretty big model. There's lots of variables. We've been working to expand it to include uncertainty around historical energy demand, as well as the non-price factors, which is a variable in the model called the MMSM0. And it's of particular interest to me. I've worked on the transportation sector for a long time, and it's a variable we use to project electric vehicle uptake. And this consumer adoption of new technologies is a big area of uncertainty. We've got a lot of when it comes to electric vehicles, there's a lot of behavioral questions like where can I charge my car? How long is my charge going to last? And things like this. So that kind of information is not well represented in the historical data, which we're calibrating on. So new technologies are a challenge for us to model, and so we need to improve our work in term as we transition to using more electricity and in our economy. And so yeah, and it shows up across all economic sectors, and so this uncertainty analysis is broadly applicable. Thank you.
So we have, excuse me, we have time for questions, and so, any questions? Oh, I'm sorry. I'm having trouble turning this on. No, I've like been pushing the button.
There's a public.
Oh.
There's switch it on.
Oh.
If I understood it correctly, the motivation was you don't have 40,000 hours of computation time.
That's right.
But you are trying to, so if you did have it, you would just simulate your model with, it's not a uniform distribution of the sensitivity range. So I wonder if you could also, for validation, just do 100 hours or just do, 100, 200, maybe on a cluster to validate, just see if the curves validate.
Yeah, it's an interesting idea. We could definitely do that. There's there's a lot of demands on our time with the emphasis on climate change and greenhouse gas emissions recently, but it's an interesting idea to explore. Thank you.
Yeah, really interested to learn about this type of work. You assume normality, and you sort of, if I understand it correctly, simulate individual equations at a time and then stick this in. And two questions there are you worried about correlations of these variables together? Do you basically assume independence? And on top of that, why assume normality? Why not do sort of a bootstrap type resampling from past observed growth rates?
These are good questions, and yes, I think we should be examining the chance for correlation between those and considering other distribution functions. Yes, thanks, Felix.
Thank you for your presentation. Just for clarification,
Sure.
Is it a bottom-up approach or top-bottom approach?
Yeah. So the core of the model is a consumer choice energy model. So it's bottom up. Yes.
Wonderful. And I wonder if it uses emission factors, and
Yes.
you have to calculate emission factors. How confident are we in those emission factors?
There's uncertainty associated with those emission factors. Yes, we're confident in the carbon content. The emission factors for methane and nitrous oxide from combustion are more uncertain. But it's as we talked about, developing this analysis would include uncertainty around emission factors and historical energy demands. So thank you.
Thank you.
I think we have time for one more. There's one more.
Yeah, thanks a lot. Really interesting. It's good to see that the energy systems models are starting to work with uncertainty. Quick question on how you calibrated your quadratic function.
Mm-hmm.
Was that all the sort of the thing you showed in the graph? Was that all the data that you used for the calibration?
This one here?
Yeah.
Yes. Yeah, it was the high scenario, the low scenario, and the reference case. So those are the blue dots that we need to calibrate the quadratic. Yes.
I mean, obviously, so you used them probably only in the final year of your.
Yeah, you've got to do it for 1 year only. Yes, that's right. Yeah.
I think in general, I mean, these relationships might hold over more than 1 year,
Mm-hmm.
and it would sort of if you did use it, including your sort of historical years potentially, then I think you'd have a lot more data to calibrate that function, because I mean here is like 6 or 7 points that probably challenge a little bit of whether you can assume a quadratic here or whether it might be more linear or these kind of things. So I think you're underselling it with the type of data that you already have.
Sure. Yeah, I think they explored using a Taylor series, a Taylor approximation, and as an alternative. But the quadratic approach seemed to produce similar results. But yeah, thank you.
Great.